Hello everyone and welcome back to this series where we're building and optimizing RAG workflows with LangGraph. There are already few videos in this series, so I would encourage you to check them out first. With that, let's dive into today's video. So today we'll look at yet another technique within query optimization, uh, and this is called as HyPE. It stands for Hypothetical Prompt Embedding. And if you're familiar or if you looked at the previous video, we looked at something called as HyDE. This stands for Hypothetical Document Embedding, and this is a very similar approach to that. So what we'll do is we'll first recap what Hype did, so we can easily build on to that intuition. So let's say you have your user query here, right? And you have your huge corpus of knowledge base or your embeddings where you have multiple documents and you're trying to retrieve the most relevant document for your user query, right? And let me do one thing. So this is here, right? Now your user query is not always the most optimized version, right? And the main aim that in fact what we have been trying to do for all the query optimization is to sort of reduce this gap. Oops. Is to reduce this gap between the user query and the context so that your given user query can retrieve the most accurate documents from your embeddings, right? So in HyDE, what we did was for a given user query, we created a document that would be a good indicator of what this prompt is trying to solve, right, or trying to query. Now using this sort of document, or like an hypothetical document, we then do a similarity search against your knowledge base and pick the most relevant ones, right? Because your user query is short, but here it is a lengthier version consisting of many keywords that can be found in this. So that's like the core idea of this, right? Now coming to hypothetical prompt embedding, if you can guess already, here the key is to create hypothetical prompts, right? So this is oops, what is this? Yeah, anyway, so what we do here is sort of work in reverse and create hypothetical prompts for each of your documents rather than creating hypothetical documents, right? So let's go to this again. You have your user query and then you have your documents, right? You have multiple documents that are chunked and embedded. I think in our case we chose a chunk size of 1000 and overlap of 200. So you have your multiple documents here. Now what we do is we create hypothetical prompts. So for each document we create n number of prompts. In our case we'll do 3, right? So we'll create 3 prompts which when asked would result in this particular answer. So in a real world scenario, if I were to pass this prompt, it would likely return this document, right? So that's the idea. Again, the core idea is to sort of reduce this gap, right? Now in this case we were trying to guess for given user query what the document could be. In this case we are trying to guess for a given document what the prompt can be, right? So I'll similarly have 3 prompts for this, 3 user prompts for this, and so on for all of them, right? Now what I'll do is I will embed these prompts in our embeddings, right? So this is something that you can do at the chunk itself, right? Initially when we did the chunking, instead of directly storing all of them in a vector base, we'll pass each of the chunk in through an LLM and create 3 questions for them and only store this questions as embeddings, right? So you will have question number 1, which let's say it's this, like where prompt 1, right? And then you'll have your prompt 2 and prompt 3. So all of this are converted into vectors and stored here. And within this document, you will remember that they also consist of many metadata, right? From page number to specific start and end tokens, so on. So within this, we'll also create one more metadata, which will be the actual document. So we'll have something called as original document, and which will consist of this particular document, right? So let's say this is document 1. So this will be D1, right? This will also be D1, and this will also be D1, right? And then you'll have your document 2, and you'll have another 3 prompts for this. So after this is done, we'll of course use our user query to look into this embeddings rather than this, right? The idea is now your user query is going to be have a better similarity score when compared with the prompts itself, right? Yeah, so once this is done, once like the sort of similarity search is done on this, we'll identify, I think, top 4 or 5 what are prompts that are good match to this, and for each of these prompts we'll pick up the metadata, which is then augmented and passed on to generate your answer. So that is essentially the how hype works, right? Now with that, let's quickly jump into our VS Code and take a look at this code, right? And we'll also try and compare it with our basic RAG. So this is typical loading all the libraries. The key step is here where we are indexing with hype, this entire step. So this is similar to what we did earlier where we did the chunking and the embeddings. Here we have a slightly different approach where we have to create questions for each of the chunk, right? So we are using OpenAI's embeddings. Choose a specific path for this embeddings to be stored. Earlier we used I think just RAG embeddings, and now I'm creating RAG embeddings hype. We can choose an LLM, like a smaller LLM, just to create questions. And the prompt here is, hey, you are a document analysis assistant. Given the following text chunk from a document, generate exactly 3 hypothetical questions that this chunk could answer. And these questions should cover the key ideas in the chunk. Respond with only 3 questions, 1 per line, no numbering or bullet points. And the input that will pass is the chunk itself, right? And this is the entire the function to create your embeddings and questions. So you define the file path where the file is stored, and we are continuing using this LLM PDF. I think we have about 15-16 pages here, and we define a loader. We're using PyPDF loader here, and these docs are loaded. I mean these the files are loaded inside docs, and then we define a text splitter where the chunk size is 1000 and overlap is 200. And when we finally apply the text splitter, these are then stored as chunks, right? Now we look at each chunk within this chunks and pass it into this like format it under this prompt and pass it to this LLM. So the LLM is invoked here, and you get your response. So the response here is going to consist of 3 questions. So we are simply stripping the questions and splitting it based on the lines to get our 3 questions inside a list, right? Now for each question in this list, we are appending our docs with the page content, and this page content is just going to be the question itself, right? And you also are storing the metadata, which is your original content, right? Which is actual document that was supposed to be there. And then we create a vector store, and using Fez we are creating these vectors consisting of your prompt questions. Next we look at the local and see if anything exists in the first place. And when you run this document, right, only the first time this will happen. If this is already there, this will run. If not, it is just going to load from your local if it is present, right? So this is like just a one-time thing, unless of course you update your parameters or update your underlying file. This only happens once. And the rest is pretty much the same that we have been doing so far. You define an LLM, you define the states, state variables. One thing extra is here matched questions, right? So we're trying to keep a record of what questions matched with your original user query. You have a prompt definition for RAG. And yeah, a little bit of change here with the nodes. You have the similar nodes, right? Your retrieval node, augmentation node, and generating node. One thing that's changed here is sorry, I had to pause, but one thing I realized was, or is that we don't have this node as such. I've just written it all under this function right over here. So the actual retrieval is already done. Yeah, so the retrieval and the hype process is sort of combined in this node called as retrieve, and then you have your augment and generate node. So within this retrieve, let's see how this goes. So first we're retrieving the top 6 prompts. Generally we looked at top four documents, but the reason we're looking at 6 prompts is because it's quite possible that since we are looking at 3 prompts each, right? It's quite possible that each of them retrieves the same document, because the content is pretty much the same. So in this case, we'll end up with having 3 documents that are duplicated and maybe 1 document that's different. So essentially 2 different documents, right? Or 2 unique documents. So for that reason, we'll extract 6 prompts. So even if there are 3 common ones, we'll still end up with more than 1 or 2 unique documents, right? So that's what is happening here. And then we do the retrieval step. So we invoke the state query, and this looks at your matched documents. Now here we are deduplicating them. So if it's having common documents, we simply remove them, and we want to keep unique sort of questions here. With that, we are then looking at getting the metadata. So what happens here is each of the individual doc in the matched questions is sort of looped, and we are retrieving the original content from it. So for each question, what was the original document within them, right? And this is then appended to your original docs, and the actual context will be formed by sort of joining each of these individual documents, which is then passed on to your state variable as context. Your augmentation step is simply formatting this RAG and adding your question and context. And finally, the generation step is passing this formatted RAG to your LLM. So this is how yeah, and the graph definition is same, right? A linear workflow, and of course, like I said, we don't have this step particularly. It's just a linear workflow here, right? And let's try this out, right? Let's say yeah, actually I've been using Claude Code recently. I've just started using it. I'm really liking it, to be honest. On a side note, if you think it would be worth making a tutorial on the usage of Claude Code, I would be happy to do so. Do let me know. Of course, I would want to test it out and extensively work with it. There are obviously many videos online already, but maybe specific to Gen AI or specific to some RAG workflows, how it can be used and so on. I'll be happy to do that, right? Yeah. So with that, let's go. And let's run this. I think this is called, yeah, I had renamed it in between. So this should be it. What we'll also do is yeah, I think I renamed the whole file, so let me copy this. um, Yep, that should run and we should have a result, and we'll go to Langsmith. That is a tracing tool that we've been using consistently. That is from LangGraph, LangChain themselves, the same community, useful for tracing your inputs, outputs um, within your LangChain, LangGraph workflows. So we got the answer here. The question was differentiate between encoder and decoder. We got the answer. Let's also maybe try our basic rag. Let's see if I have the same question there. I don't think so. I'm going to copy this and let's also run a basic workflow uh, just to compare the two processes, um, and not necessarily the answer, because the answers are going to vary based on the questions, and sometimes your basic encoder might do a good job itself. It looks like it's not got any answer for decoder, but yeah, let's see. Let's go to our Langsmith. All the tracings are done under RAG with LangGraph. We'll look at our the what was that? We'll look at the hype variant first. So with hype variant, you have your retrieval, right? And let's look at the documents it has retrieved. But more importantly, we want to look at the questions that it had generated, right? Yeah, so let's look here at that main step. You have your answer, that's fine. Your augmented query, that's still fine. Your context, query. Yeah, so this was a query, differentiate between encoder and decoder, and we've got a six prompts, which were the prompts generated for its underlying document, right? So what role does the encoder play in transformer architecture? What role does decoder play in the translation process? What role does encoder play in transforming source language? What does encoder model function? What is the main focus of the encoder? How does the decoder generate? Looks like it has done a decent match, right? It was able to match between these two. I don't know if we have, yeah, let's maybe look at the underlying documents itself, right? Now if you see, of course, these has these wordings, decoder, decoder, encoder. So normally also it should be able to do a good job, but because now we have identified the ideal prompt for each of this document, it's able to directly match with that itself instead of trying to find a similarity score in a whole big document. That's like the kind of idea of this, to match um, with the prompt of the underlying document. Let's see how the other prompt worked, or yeah, how the basic RAG workflow worked. Here we have the retrieval step. So let's see. I think did it pick the same one? Encoder simplifies. Yeah, this document was the same, right? Yeah. But look at it, no? The first one, the first document that it thinks to be um, uh, accurate, it didn't really have many context here. I think there's just decoder, encoder. I don't think there's a lot of information from here that can be added. Um, but that's all. We don't have a good representative of this here. So in the hype variant, it was the prompt that we created, right? Like the user questions, the prompt that we created for each of this document um, acted like a sort of a filter that can be easily searched up against. So yeah, that's in essence how hype works. I hope this video was helpful. the all the code files and snippets, everything is there in the GitHub repo, which is the link to which is in the description. Do let me know how you're finding the series, and if you have any questions, drop it in the comments below, or you can also reach out to me on LinkedIn, and I'm quite active there, so yeah, happy to help. Thank you, and we'll see another optimization technique in the next video. Thanks again.